Bismillah ar-Rahman ar-Rahim. We have a zero mean random variable x, and its fourth moment is strictly positive and is finite. We are interested in lower bounding the probability that x is strictly greater than zero. X is strictly positive. And the lower bound makes use of the second moment of x and the fourth moment of x. Because of this assumption here, both are strictly positive and finite. Now, can it be the case that the probability that x greater than zero, that this probability is exactly equal to zero? Let's see the implications of this. This implies that the probability that x is less than or equal to zero is 1. This means that random variable x is non-negative almost surely. Probability that x is strictly less than 0 is the probability that minus x is strictly positive. This probability can be written as the probability of the union k is a positive integer minus x greater than or equal to 1 over k. Because if minus x is greater than or equal to 1 over k for some k, and k is a positive integer, then minus x is greater than 0. And if minus x is greater than 0, then there must be a positive integer m such that minus x is greater than or equal to 1 over m. Now let's apply continuity of probability. The probability of this union is the limit as k tends to infinity, probability that minus x is greater than or equal to 1 over k. Minus x is a non-negative random variable. We can apply here the Markov inequality. And so this is limit k tends to infinity, the expectation of minus x divided by 1 over k. So this is equal to minus limit k tends to infinity, k expectation of x. But x is a zero mean random variable. So this is limit k tends to infinity of the all zero sequence, and so this limit is equal to 0. So if we assume that the probability of x being strictly positive is 0, then x is non-positive with probability 1. But then x is strictly negative with probability 0. So this means that the probability that x is equal to 0 is 1. So a zero mean random variable that is strictly positive with probability 0 is in fact a degenerate random variable that is equal to 0 almost surely. Okay. And so our case will be when the probability of x being strictly positive is strictly positive. And indeed, our objective here is to have this as a lower bound on the probability that x is greater than 0. Okay, so our interest is when the probability that x greater than 0 is greater than 0. If this is not true, then as we have seen, then x is simply the random variable that is equal to 0 with probability 1. How can we prove our inequality here? So let's start by expectation of x squared. And let's write it as expectation of x squared, indicator x greater than 0, plus expectation of x squared, indicator x less than or equal to 0. X squared is multiplied by 1 here, And 1 is indicator x greater than 0 plus indicator x less than or equal to 0. And then by the linearity of expectation, we can separate this expectation into 2. For this term here, we employ the Cauchy-Schwarz inequality. So Cauchy-Schwarz. And so the expectation of this product, x squared times the indicator, is less than or equal to the product of these two square roots. Here we have the expectation of x squared squared, that's x to the 4. And here we have the expectation of the indicator squared. Well, the indicator is 0 or 1, and so the square is also the indicator. And so this is the square root of the fourth moment of our zero mean random variable x. And the expectation of the indicator is the probability that x is strictly positive and it is raised to the power 1 over 2. So let's have this. This will be 1. Now we need to handle the other term. What can we do? Let S be the absolute value of x, indicator that x is less than or equal to 0. And because the indicator is 0 or 1, this is less than or equal to the absolute value of x. Now, the expectation of the square of the absolute value of x times the indicator, so this is the expectation of x squared, indicator, x less than or equal to 0. This is the expectation of s squared. Now for the expectation of s squared, we will write it as expectation of s to the power 2/3 times s to the power 4 over 3, like this. And this is in preparation for the application of Holder's inequality. So we'll take this and apply Holder. And for Holder inequality, what do we have? If we have two non-negative random variables a and b, then the expectation of ab is less than or equal to the expectation of a to the power p to the power 1 over p. Then the expectation of b to the power q to the power 1 over q. And this is for b greater than 1, q greater than 1, and 1 over b plus 1 over q is less than 1. So let's apply Holder inequality in our case here. We will choose b to be 3 over 2, so that when this s to the 2/3 is raised to the power p, which is 3 over 2, we get expectation of s. Now, if p is equal to 3 over 2, then q is equal to 3, such that we satisfy that 1 over p plus 1 over q is unity. And in this case, we will have expectation of s to the power 2/3 to the power 3 over 2, that's s. And we need to raise here to the power 2 over 3, 1 over p. And then we have another expectation, and this s to the power 4/3 will be raised to the power 3. Now we have s to the power 4. And we need to put here 1 over q, which is 1/3 in our case. Note from the definition of s, it's the magnitude of x times this indicator. So s is less than or equal to the magnitude of x. So s to the power 4, okay, so we have, by how we define s, we have s to the power 4 is less than or equal to x to the power 4. And we get as an upper bound expectation of s to the power 2 over 3, expectation of x to the power 4 to the power 1 over 3. Okay, and this is 2. Note that our choice for this particular application of the Holder's inequality is so that we get s to the power 4, because s to the power 4 can be upper bounded by x to the power 4. And don't forget that our main task is to construct a positive lower bound on the probability of x being strictly positive, and it makes use of the second moment, and we have here the fourth moment in the denominator. So we want the fourth moment to appear, and this is one way of doing this. And now we have the expectation of s. Now the expectation of s is not the expectation of x, but let's see whether they can be related in a useful way. X is zero mean random variable, that's a given. So expectation x is equal to 0. Now I can write down this expectation again by taking x, and then I have indicator that x is greater than 0 plus indicator that x is non-positive. And applying the linearity of expectation, this is expectation x indicator that x is greater than 0 plus expectation that x, and then we have indicator that x is less than or equal to 0. Okay. Now we have that minus x indicator x less than or equal to 0 is equal to the expectation of x indicator that x is less than or equal to 0. Now, if x is strictly positive, then this indicator is 0, that indicator is 0, and basically we have 0 equals 0. Now, if x is less than or equal to 0, then both indicators are equal to 1. And in this case, when x is less than or equal to 0, it is indeed that the magnitude of x is equal to minus x. Okay. But this is exactly our friend here, big S. So this is equal to big. So big S can be written in another way. It can be written as minus x indicator x less than or equal to 0. Note that, so, the expectation of S is the expectation of this, which is minus expectation of x indicator x less than or equal to 0. But note that these two terms, this expectation and this expectation, which is what we have here with a minus sign, the sum is equal to 0 because x is a zero mean random variable. So if we move this to the other side, it becomes minus expectation x indicator x less than or equal to 0. So from the zero mean property of random variable x, this is equal to expectation of x indicator x greater than 0. So this is another useful way for writing down the expectation of random variable big X. It is expectation of x indicator x strictly greater than 0. Now we'll try to upper bound. Note that, again, in obtaining equation 2, we have the expectation, we have the expectation of S here. We have this term here, and basically what we are trying to do is to have an upper bound on this expectation using the moments of random variable x. So let's apply Holder's inequality again. So expectation of S is equal to the expectation of x indicator x strictly positive, and then let's employ our friend Holder again. We need to make choice for P and Q, the desired lower bound on the probability of X being positive, it involves, as I said, the fourth moment. And so perhaps it's a good idea to use P equal to 4 so that when we employ Holder's inequality, this X becomes raised to the power 4. And if P is equal to 4, because 1 over P plus 1 over Q is unity, then Q must be equal to 4/3. In this case, we have an upper bound in the form of a product. This product will be raised to the power 1/4, and this other guy will be raised to the power 3/4. Here we have the expectation of X raised to the power 4. And here we have the expectation of the indicator raised to the power Q, but the indicator is 0 or 1. So it is itself. Raised to the power Q is the indicator of X greater than 0. And this is expectation of X to the 4 to the power 1 over 4. And this expectation of the indicator is the probability of interest, the probability that X is strictly positive. Now it is raised to the power 3 over 4. So this is an upper bound on the expectation of S using the fourth moment of X, and we also have this probability. So let's go back to equation 2. So here we have expectation of S squared is upper bounded by this. Okay, so from 2, let's rewrite it. We have expectation of S squared is upper bounded by the expectation of S raised to the power 2 over 3, and then the fourth moment of X raised to the power 1 over 3. Let's make sure that I wrote it correctly. So here it is. Now we have a further step in which the expectation of S is upper bounded by this product here. So here we have the expectation of S to the power 2/3. So this is upper bounded by the expectation of X to the 4. And then we have 2 over 3 times 1 times 1 over 4. That's 1 over 6. And then we have probability X greater than 0. Then we have 3 over 4 times 2 over 3. So this will give us 1 over 2. And then we have this guy, copy and paste here, expectation X to the 4, 1 over 3. So let's combine these two. So this is equal to the expectation of X to the 4, 1/6 plus 1/3. This is 1/2. And then we have probability that X greater than 0 raised to the power 1 over 2. S is the absolute value of X, indicator that X is less than or equal to 0. Expectation of X squared, indicator X less than or equal to 0. This is upper bounded by the square root of the fourth moment of X times the square root of the probability that X is strictly positive. Okay. So this is inequality 3. Started with expectation of X squared. And we split that expectation into an expectation of X squared times the indicator that X is strictly positive. Now using Cauchy-Schwarz, which is a special case of the Holder's inequality with P equals to 2 and Q equals to 2, we obtained that this term here is upper bounded by the expectation of X to the 4 to the 1/2 times the probability that X greater than 0 also raised to the power 1/2. Then we studied this term here by defining S to be magnitude X, indicator X less than or equal to 0. So the square of S is X squared, indicator X less than or equal to 0. We obtained an upper bound on this term. So we can have an upper bound on X squared using inequality 1 and using inequality 3. Using 1 and 3, expectation X squared is less than or equal to expectation of X to the 4 to the power 1 over 2, probability X greater than 0 to the power 1 over 2. And actually the two upper bounds, this one in inequality 3 and inequality 1, are the same. We can just multiply by 2. To eliminate the square roots, we can square all sides. So this will be expectation X to the 4, probability X greater than 0, and this 2 becomes 4. Now we have our desired lower bound. The probability that X is strictly positive is greater than or equal to the square of the second moment of this zero mean random variable X divided by 4 times the fourth moment of X.